Okay. Thank you everyone to join us today. Today we will talk about enabling diverse workload scheduling in ER. I'm Wanda. I'm currently working at Hot and Watts. I'm Hadoop committer. Currently, spend most of time working on scheduler enhancements. Before I joined Hot and Watts, I worked in Pivotal and Alibaba. Yeah.
I'm Craig Welch. I'm a Yarn contributor. I also work mostly on the scheduler and some other things from time to time. Before that, I was a Yarn and Hadoop user at Disney, where I worked on some analytics projects there.
All right, let's get started. So Hadoop and Yarn is a home of big data processing. We have very different workloads. For example, we have services like Terminal and HBase. We have a batch job like MapReduce and Giraffe. Also, we have interactive and real-time jobs like TEDS and Spark. All of them have very different, crazy requirements. Someone says, I want to be fast when the cluster is full. And someone says, don't take away my resources. And somebody wants to schedule a huge job at a specific time. We want to make them as happy as possible to run together in Yarn, not fight with each other. So let's get started. This is agenda today. First, I will talk about overview. Majorly, it's a background about this talk and several enhancements we have to enable diversified workload scheduling. A little bit background. Currently, resources are managed by hierarchy of queues. For example, you have a company, and company has a big cluster. You have several departments. For example, you have R&D department, and you have a sales department. Each of them shares 50% of the cluster. And under the R&D department, you can have a QE team and dev team. So we have 5 nodes in cluster, in this cluster, all right? So N1 to N5, each of them has 10 GB of resource and 10 CPU cores. So totally we have 50 GB of resource and 50 of CPU cores. So as an example, sales department takes half of the cluster resource. So it can use 25 of the gigabyte and 25 of the CPU cores. One queue can run multiple applications. I think most of you should know this. Right? For one application, there can have run several containers. One container is a bundle of resource. You can have, for example, here you can see the container has 2 GB of memory, 2 CPU cores, and some network bandwidth. And one container can related to some real process. So here you can see the container runs some MapReduce task. Right? There are some general suggestions about how to manage your workloads by queues. First, you can by organization. So you can manage them by different organizations, by different departments, by different teams. You can make it a hierarchy of queues. And also, you can make them by workload. You can have an interactive queue and have a batch queue. So each of them has some portion of share of the cluster resource. So they will not fight with each other. If you have a very big cluster and you have some different kinds of workload, you can make a hybrid one. So under each organization, you can have batch queue, interactive queue, real-time queue. All right. I will talk about several enhancements we have. First is node label. There are different types of node labels. We have node partition. This is available since 2.6. And we have node constraint. This one is still work in progress. Today I will majorly focus on the load partition. One node can belongs to one partition in the load partition world. This is related to resource planning. So I will talk about how the resource planning is related to the load partition later. Here we can see an example. We have 5 nodes in the cluster, H1 to H5. H1, H2 belongs to the GPU partition. And H3 and H4 belongs to large memory partition. And H5 belongs to default partition. So if you don't specify a node belongs to some partition, it belongs to default partition. And also, we can have load constraint. One node can assign multiple constraints. For example, here you can say H2 has a Windows constraint and also JDK8 constraint. This is about how resource planning related to load partition. So with load partition, we can specify different queues has different share of resource under each partition. So here you can say the sales queue under GPU partition have a 70% of share, and sales under default partition have a 20% of share. And also, it is possible for you to specify some partition will only be used by some specific queues. You don't want anybody else to use it. So here you can say the large memory partition only can be used by sales team. So basically, load partition is makes one cluster dimension to be multiple dimensions. You can specify different capacities of queues under different partitions. This is an example about what is exclusive node label node partition and what is non-exclusive node partition. So below one is a user, or you can think about it as some application. The Slate application wants to have a resource under the Slate partition. And the bear wants to resource under bear partition. And some users don't care which partition it is runs, so it says, I don't care. In exclusive world, the Slate goes to Slate partition, bear goes to bear partition, and I don't care user goes to default partition. This is basically wants to isolate a resource because maybe Slate and the bear user don't want anybody else to use their resource. In the non-exclusive world, the I don't care user can be allocated to the Slate partition as well as bear partition. But when the partition has idle resource, if the Slate user or the bear user comes back, ask more resource, and the Slate partition is already full, the I don't care user will be taken out. There are some general use cases and best practice of load partition. First, it is dedicated nodes to run important services. For example, you can run an H-based region server using Apache Slider under some node with SSDs, which can get better performance. And also, you can have nodes with special hardware in the cluster and only used by some applications. Also, if you want better utilization, you can use non-exclusive node label so that users can use it when the partition is idle. You will not waste of the load. And also, please be careful about user limit capacity of the queues to make sure your job will be launched. I will cover much more details about the load label in tomorrow morning's session with Mac, so welcome to join. About resource preemption. So in Compact Scheduler, each queue have a configured minimum resource. For example, here we can say the A queue has 20% of minimum share of the cluster resource, B has 30, C has 50. Since it is a minimum share, so some people can use more than its minimum share if you allow them to do. So preemption policy here is to use to when some queue is under its minimum capacity, and somebody else is more than its minimum capacity, the preemption policy will preempt resource from the queues used more than its guaranteed resource for the queues under its guaranteed resource. So this is to ensure SLA. I will give an example about this. So here we can see when the preemption is not enabled, which is a above picture, we have two queues, Q1 and Q2, two applications, app1, app2, running in different queues, right? And we assume the Q1 and Q2 has a same configured minimum capacity, so they can each of them can get at least half of the capacity in the cluster. So the app1 submit first, it is get started and running, takes all the resource in the cluster. And in T1, we submit application 2. And application 2, after it is submitted, it cannot get resource immediately because all the resource is taken by application 1. So the application 2 can get a resource after a while. And it can only take a little resource because it depends on how the application 1 release resource. After a while, application 1 release more resource, so application 2 can take more resource. At time T2, application 1 finished. Application 2 takes all the resource in the cluster, and in the time T3, application 2 finishes. When we enable the preemption, after the T1 application 2 submitted, the preemption policy will preempt resource from application 1, so that the application 2 can take half of the resource of the cluster, and it can start running. So we can see the application 1 in this case can finish earlier than when the preemption is not enabled. This is to ensure SLAs of the Q2. There are some best practice of the resource preemption. There are some configurations to control pace of preemption. First is the max wait before kill. This one is to when a container is max will be killed by resource manager. The resource manager will wait for some time before kill the container. This is to make sure application can save state of the container. When you increase this value, it actually it can not preempt container too aggressively. And the second thing is total preemption per round. This is to control how much container you will preempt in each time unit. And the natural termination factor is when you match some container will be preempted, you will only preempt some certain percent of container. For example, you only want preempt 50% of the container in each time unit. So this is also to control the pace of preemption. There are also some configurations to control when and if the preemption happens. You can set the max ignore over capacity. This is to preempt queues when the queue is over a certain number of its minimum capacity. And also, you can disable preemption for some queues because some queues may run some very important workload. You don't want to preempt such workload. Okay, I will talk about the reservation system. This one actually is have a today's morning. There is one session about that, so I hope you don't come to that session. Some overview of reservation system. Reservation system is to reserve resource ahead of time, as a name. So it's very similar to ordering a table in a restaurant. You go to a restaurant, you say, I want a table for X person at Y time. And the waiter will check its timetable to say, all right, I can take this reservation. And after some time, a waiter will come back to you to say, sir, your table is ready. So reservation system does very similar things. Application will send a reservation request to resource manager. And the resource manager will check the timetable if the reservation can be scheduled or not. If it can be scheduled, it will return you a reservation ID. And after time, resource manager will notify you, and you can start to use the resource. This is to enable more predictable start and finish time of some time-critical jobs. Some use cases of the reservation system. First thing is Gantt scheduling. Currently, Yarn can do. First, I think I should talk about what is Gantt scheduling. Gantt scheduling is an application wants some maybe 10 gigabyte of resource. The application cannot make any progress before the 10 gigabyte of resource are all given to you. So currently, Yarn can do this by application master can continuous ask resource from resource manager, and the resource manager will return some resource to the application master. The application master will holding resource until it meets the requirement. So in this case, if you were doing the holding resource in application master side, a resource could be wasted, and there potentially have risk of deadlocks. So here is one example. Giraffe is an Apache project doing the Gantt scheduling. When the cluster is idle, is dedicated, you can see the dotted line. We can run in the Giraffe very smoothly. It can get started, get all the resource, and finishes. And it is very beautiful as a rectangle. And when the cluster has some other workloads, for example, we have a sort job. The red line is running, and after a while, we submit our Gantt scheduling job, which is a Giraffe job. And the Giraffe job will start into holding resource. You can see the shadow part. It's a Giraffe job is holding resource. And after some time, it gets enough resource to start running. But you can see the shadow part is totally wasted resource. This part of resource cannot used by anybody. It's just held by the application master. So reservation system can solve part of the problem. Actually, it lays the foundation of the Gantt scheduling. And also, it is supposed to do in workflow. For example, you want to run jobs in stages. The first stage wants to starting to run at 1 a.m. Needs 10K containers. And stage 2 is after stage 1. Needs 5K containers. Stage 3 after stage 2 is 2K container. This is very similar to the DAT program that the TEDS or MapReduce has a very similar behavior. So you can submit such resource reservation request to reservation system. So it will figure out. There is some results and reference here. So this is a report from Microsoft Research. Actually, Microsoft Research is a major contributor of this feature. So the red line and the green line are not enable reservation. So the job can, you can see the utilization is not good enough. And when the reservation is enabled, you can see the blue line. It's very good. It's almost 100%. There are some more reference you can take a look. You can see the discussion and report in ER 1051. And you can see some details about how to use it, how to leverage the reservation system. There is some example in the ER 2609. All right, so I will, Creed will continue to talk about some other features we have. Yeah.
Thanks. Okay, so the first thing I'm going to talk about is pluggable scheduler behavior. And the first thing that might be interesting to find out is why do we want this kind of an addition to Yarn? So today, it's kind of difficult to share functionality between schedulers. There's no established framework, no established interfaces, other than the very high-level Yarn scheduler interface that allow multiple schedulers to have the same kind of code sitting behind their functionality. And so the result of that is that it's difficult for users using different schedulers to achieve the same kind of behavior. And fixes that might be relevant across schedulers, they tend to end up in one or the other of the two, or the multiple schedulers that are available, and not in all of the schedulers that might need them. And then finally, from kind of a different perspective, there aren't simple or well-defined mechanisms that exist to allow you to mix and match functionality within a given cluster. So this might make more sense later on when I talk about the ordering policy, but if you have multiple points of entry, like multiple queues, you might want them to actually have different kinds of behavior. And having a encapsulated mechanism for controlling that behavior as a plugin makes it easy for you to set them up in distinct ways, all within the same cluster. And so one of the solutions that's available and what we're looking at doing and have started to do is move to a shareable or a pluggable scheduler mechanism for determining the scheduler's behavior. So the goal is, again, to recast the behavior of the schedulers as much as possible as policies that are specific to particular functionalities and shareable across schedulers. Some of the candidates for this are resource limits for applications and for users, and then what we're going to talk about a little bit more, which is ordering policies for the ordering of allocation and preemption of containers to and from applications. With this kind of functionality, we can maximize the feature availability across the schedulers and reduce fragmentation between the schedulers. And we can also configure different queues for different kinds of workloads all within the same cluster. And as easy as putting things together with Legos. So the specific first policy that we've put into place for the capacity scheduler side of things is the ordering policy. And this is configured at the leaf queue level. It's currently available in the capacity scheduler. There's an intention to make the functionality available in the fair scheduler in a similar fashion. And again, it allows implementation of different policies for ordering assignment and preemption of containers for applications. So taking a step back, when an application is running in the cluster, a Yarn application, which includes MapReduce, Hive, what have you, anything that runs in the cluster really, what they do is they say, I need so many containers of so much of a size. I need these resources in order to continue. One of the various things that are in play that determine when an application gets these resources is the order in which applications are being presented with the resources when they become available. So typically in the capacity scheduler, this is when the node heartbeats. So when a node heartbeats to the scheduler, it says, hey, I've got this much available, and the scheduler is going to pick the queue and then the application within the queue that's going to get the resources from that node. So the ordering is very important in determining which of these applications is going to be making progress at any given point in time. The initial implementation for the ordering policy is FIFO, first in, first out, which is the classic behavior of the capacity scheduler. The first application that starts gets as many resources as it wants that the queue can provide it with until it finishes. And then the fair scheduler, which we'll talk about more in just a second, which attempts to balance and allow multiple applications to make concurrent progress. It's important to understand that user limits and queue capacity limits are still respected. So one of the differences between this and policy configurations that can be plugged into, say, the fair scheduler today is that it's something of an all or nothing proposition. All of the behaviors are part of those policies. In this case, we consciously made the choice to say, hey, this is specific to ordering of allocation, and these other kinds of things like limits will be different types of plugins so that you can mix them together and so that you can specify them for individual queues. So the FIFO behavior already existed. We just re-encapsulated it as an ordering policy. But fairness for applications is something which is new to the capacity scheduler. So we based our fair ordering policy on the fair sharing logic that exists in the fair scheduler as one of its overall policies for behavior. Both of them work in a similar fashion. They assign containers to applications in the order of the least to greatest resource usage at any given point in time. The idea is you can think of this as almost like a sorting, as a bubbling up, where an application which is underserved, which is using less resources, is going to go ahead and get first dibs at new resources. An application that, in fact, doesn't need any more resources is just going to pass that by and it's going to move on to others. But in this way, an application that has more resources gets put behind applications that have less resources, which allows them to sort of bounce up and down, and all of them get a share of the resources at any given point in time, and they can make concurrent progress as a result. And one of the other advantages of this is that if you have an ad hoc queue or a queue which is being used largely for exploratory activity, it allows all of these jobs to run at the same time, and no one has to wait behind anyone else in order to get started and to make progress. Rather than someone starting and moving to the finish as quickly as possible, all of these users get sort of a fair share of the queue, and they can all make progress together. Given that, there are these different kinds of policies, one of the obvious questions is going to be, when should I use which policy? We have more than one policy for a reason. So there's sort of rough guidelines. It's something that you have to consider in more detail because not every use case falls into these simple small categories, but these are fairly typical categories for the kinds of jobs that you need to run, or the kinds of sets of jobs, rather, not individual jobs that you need to run. So if you have a queue that is mostly going to be used for on-demand or interactive or exploratory or ad hoc queries where your analysts are just exploring the data, for example, you're probably going to want a fair sharing policy because that ensures that no one is stuck waiting behind someone else for their job to finish. Everybody can kind of work together, share the resources, make progress together, and no one is sitting there waiting for resources on someone else. If you want to have a more predictable recurring batch type queue, and this is especially true if you're externally coordinating the order in which you run jobs and you want them to run as quickly as possible, you're probably going to want to have a FIFO type policy. Generally, this allows individual jobs to finish as quickly as possible because they're able to get all the resources available to the queue to use as far as they can use them, and they don't tend to end up waiting on other bits of work to finish that could be happening concurrently. You can just think of FIFO as giving the top application the most possible concurrency at any given point in time, which tends to speed its completion. If you have a mix of the two and you don't want to separate them into different queues, you probably will want to go with the FAIR policy. It does allow the bigger jobs or batch jobs to run just fine, but you'll also get the benefits of having people who are doing exploratory work not wait behind those big jobs before they get to do what they need to do. Some of the configuration points, the configuration of the ordering policy is per queue. So you've set it in the capacity scheduler configuration in the way that's available up there with the name of the queue there, and then you can choose at the moment FAIR or FIFO. There may be other implementations available in the future. And then there's a specific setting for the FAIR policy, which doesn't apply to the FIFO policy, which is size-based weight. Size-based weight, so as you can tell probably from the earlier explanation of what the fairness algorithm is and how it works, it does tend to favor small applications. And if you have a large number of small applications popping in and out of a queue with a smaller number of large applications running a long period of time in the background, it's conceivable that you could have a starvation scenario. A couple of options for avoiding that starvation are to split these different types of jobs into different queues, or the other is to go ahead and enable size-based weight. Basically, size-based weight reduces the apparent usage for a larger application so that natural boosting that the algorithm tends to do is a bit stunted, and it allows those larger applications to avoid starvation in many cases. So, another area where there's been a fair bit of work in Yarn is support for Docker containers and potentially other containers. There have been some talks that are more dedicated to Docker containers, so this is kind of just a quick overview of what that is and how that helps you in terms of your workflow with Yarn. Containers, for background, I think probably most people are familiar with containers. They've kind of exploded in importance and popularity recently. But just quickly, a container is sort of it's a virtualized machine image that when you launch a container, wherever, there are many different container management systems out there, or rather overall systems within which you can run containers, Docker, for example. It looks like a single machine image to the application that's running, and the rest of whatever may be involved with whatever system it's been virtualized on is irrelevant. It gets its own file system, its own set of libraries, its own versions of everything, its own process tree. It's a little virtual machine running with its own file system. So that is very attractive for a number of reasons. One of the big things that make it nice is that if you have complex dependencies, or you want a higher level of sandboxing between whatever you're running inside your container and whatever else might be running on the machine for security and other reasons, this gives you a lot of functionality in that regard. And one of the benefits of bringing this to Hadoop is obviously you've already got these big Hadoop clusters, and it's another opportunity for you to share that investment amongst all kinds of different workloads instead of being limited specifically to the classical Hadoop workloads. So what's the status of Docker container support today in Yarn and what's coming up? So sometime in the past, the initial sort of exploratory implementation was bringing Kubernetes to Yarn. And Kubernetes is out of Google. It's an existing way to handle containers, including Docker. And the initial version was really just saying, hey, this is a new application master, which is sort of the coordinator for a particular job. And it would go ahead and launch things using basically the functionality of Kubernetes. It was not highly integrated into Yarn, which was a drawback, but it was a quick way to get started. The second level was a custom container launcher for Docker containers. So this embedded the ability to support containers more firmly in Yarn, made it more of a first-class citizen of Yarn. But because of the nature of the way in which container launchers are configured historically in Yarn, you could only pick one kind of container launcher. So you could use your cluster for Docker, or you could use your cluster for MapReduce and other, legacy applications or standard applications for Hadoop, rather, not really legacy. But you couldn't really do both at the same time, which obviously somewhat defeats the purpose. So the next phase, which is currently a work in progress and it's coming along well, is to get to the point that you would want to get to really be able to use Docker on Yarn, which is to be able to allow your standard containers to run alongside Docker and other containers using the term container in too many different ways. But being able to run Docker containers and standard Hadoop containers side by side. And so the final topic for today is to talk a little bit about the different kinds of resources that Yarn is aware of when it's doing its scheduling. And in this case, we're going to talk about CPU in addition to memory. So historically, Hadoop really has thought about scheduling and apportioning out resources and scheduling resources in terms of memory. And that's for a very good reason that is typically the major limiting factor for the way in which processes run in Hadoop. However, surprise, surprise, there are some workloads that are CPU intensive out there in the world. And without allowing Yarn to be aware of this, there are several disadvantages. You might end up with nodes that are CPU bound because they've gotten all of the containers that need a lot of CPU. Or cluster-wide, you might be failing to spread out the CPU load amongst nodes, and you have underutilized nodes, which could be put to better use to get your jobs done more quickly. So CPU awareness at the scheduler level is enabled by selecting the dominant resource calculator for the scheduler calculator. The default resource calculator is not aware, well, it's aware of CPU, but it doesn't use it in any of its comparisons. The dominant resource calculator does. The term dominant, in very simple terms, because it's much more sophisticated than this, but the basic notion is it takes the dominant factor in any given calculation or comparison, and it uses that to determine which is going to be the limiting factor. So, for example, if there's enough memory for something to run, but there's not enough CPU, then the answer is going to be no, because the limiting factor in that case is the CPU. Right? And there's a reference to the paper there that gives a whole lot more detail in terms of the actual way in which those calculations, especially the comparisons are relatively simple, but the calculations are not. And finally, what does this mean in Yarn? How do you configure this in Yarn? So the unit used to abstract a CPU to indicate for a given node how many CPUs does this node have is called the vCore. The reason it's called the vCore is that there may not always be a one-to-one relationship cluster-wide between the notion of a CPU resource and the actual amount of CPU that you want to allow the system to believe it has available to it on the node. Typically, you do configure vCores one-to-one with physical CPUs in the cluster. But if some nodes are, say, newer, they're from a newer generation, or they're just more powerful because they were purchased with more CPUs, for example, you can turn up the number of virtual cores for those nodes to make up for the fact that they actually have more CPU power available to be used by jobs. So with that, Langdon and I will be happy to take any questions you might have about any part of the presentation.
Yeah.
If you can use the microphone, that would be great. If it's a 10-mile journey and you'd rather not, you can try and shout it out and we'll repeat it for you. Can you what? Yeah, I believe that his question is, can you have basically fractional cores? I believe that those are configured all as whole numbers of
yeah.
V cores. Yeah, yeah. So what you might do in that case is you might multiply the number of cores so that you can get to the point where you have the fractional. They are virtual. They are just relative. So you can run them up, multiply them up until you have what you need for your granularity. Yeah. Doesn't keep you from doing anything. It might be slightly less convenient. Yeah.
Okay, so I basically have the same question, but so are you saying that if my cluster has 100 cores, I could actually say, I could define it that it has 1,000, and that way I have fractional association?
Yeah, you could.
Okay.
The wisdom of that, you would have to think about it. What you have to understand is if you do something like that, then whatever's asking for those resources is going to need to have some awareness. So in other words, if something thinks it needs one CPU, so a typical map job, right? A mapper is going to think it needs a CPU, right? So if you say, oh, this node has 500 CPUs in it, right? But it really only has 2, that could be problematic. So doing it to really high numbers of multiples is probably not a good idea. It's okay to do it in small ways to achieve like the relatively small delta that he had in mind, but I think you wouldn't want to say it has 10,000 cores when it has 10.
Yeah, that was kind of an absurd example there.
Yeah.
But my big concern was just the ability to throttle a given job that wants to consume all of my memory.
Right.
So.
Well, so there are kind of two parts to that. One is, so when it actually gets down to what's running on a particular node, the difference in the number of cores that are being asked for when the container is being scheduled actually just sets the priority in the Linux C groups for that particular process. So if you have 2 different containers running on a node, and one said I needed 5 cores, and the other said I needed 2 cores, what actually happens in the expression when it's running in the operating system is the one that said it needed 5 cores has a higher priority. There is some notion of being more specific and having some more specific logic to link those up, but today those are done basically by priority within the C groups on the operating system. Any other questions? Okay.
Yeah, all right.
Thank you very much for coming.
Thank you.